Welcome to everybody. We are glad to have here at the University of Milano Bicocca Dr. Stephen Scott, Director of Statistics Research at Google, for this vibrant event organized by the Department of Statistics and Quantitative Methods with the contribution of the Innovation Pub. Dr. Scott received his PhD from the Harvard Statistics Department in 1998, served on the faculty of the University of Southern California at the Marshall School of Business, then became the Director of Statistical Analysis at Capital One, and finally joined Google in 2008. Dr. Scott is here this afternoon after an intense week in Como, where he gave lectures on Thompson sampling, regression modeling, and sparsity, time series modeling, and application with case studies, such as causal impact, nowcasting, forecasting, and finally this morning on how to face big data. It has been a deep and exciting journey. I discovered through Stephen Scott that active research at Google explores virtually all aspects of machine learning and optimization challenges related to search, advertisement, social, and also Google infrastructure. I also learned from him that Google has a large number of interdisciplinary collaboration with scientists from academic institutions, and a real virtual team has produced about 1,000 scientific papers up to now on hot topics like the one I mentioned, and coping with the major challenge of solving problems at very large scales. Dr. Scott will give a talk on predicting the present with Bayesian structural time series that will surely provide us a glimpse on the vast scenario he works on. So I thank Dr. Scott for accepting our invitation.
Well, let me first just say thank you for that wonderful introduction, and I want to thank all of you for being here today. I believe that this is a holiday period for the school, and so I'm a little surprised to see the room as full as it is, but I'm very, very gratified that you all took time out of your days to come hear this speech. The title of my presentation is Predicting the Present with Bayesian Structural Time Series, and this is joint work with my boss at Google, whose name is Hal Varian. And those of you from the economics side of the school are probably familiar with Hal Varian. He's a very well-known economist. He's the chief economist at Google. And a lot of the ideas that you'll see here today are his ideas. I helped flesh out some of his ideas with some of the more technical material. Predicting the present sounds like a strange thing to do, right? Why would you have to predict the present? Well, the present has already happened. Another name for predicting the present is sometimes called nowcasting. So you know what forecasting is, right? Forecasting is making predictions about what's going to happen in the future. Nowcasting is making predictions about something that's already happened. One reason you might want to do nowcasting is because the something that has already happened has happened, but it hasn't been recorded yet. It hasn't been reported yet. It hasn't been released yet. This is a phenomenon that happens frequently with official government statistics, and because my boss is an economist, we focus on official government economic statistics. I have showing on the slide right here an example of an economic time series. This is a particularly important economic time series. This is the time series of initial claims for unemployment in the United States. The reason this is a particularly important time series is that initial claims for unemployment is one of the factors that economists use when they all get together in their big meeting and decide whether or not we're in a recession. So it's a very important number. This particular series is released weekly, which is very fast for economic data. There's economic time series that are important, but they're only released maybe once a month, and there's some others that are released only once a quarter. In our current environment where we get to see data move in real time, waiting until the end of the quarter is sort of seems like waiting for the glaciers to melt or something like that when you're waiting for the data to be released. And so the idea of nowcasting is once the quarter has ended, it's going to take the government a while to accumulate all the data and run it through their models, and eventually, so the quarter's ended, but it might still be a couple weeks before the series is released. Meanwhile, there's some other data that you think might be related to initial claims for unemployment or consumer confidence or any of these things that you could maybe use to help make a prediction for what that number is going to be once it is released. So when you look at the series that I have on the board, you'll notice that first you'll notice it's data that evolves over time, right? So it's a time series. And when you look at the time series, you'll notice that it has some structure to it. You can see the incidence of the financial crisis, the financial meltdown which occurred because of a housing crisis in the United States. You can definitely see when that happened and the impact that it had on the initial claims numbers. You can also see that, so you might be inclined to call that change a trend in the series. So this is one element of structure in the data. You'll also notice that there's a pretty strong seasonal pattern in the data. Every year it looks like there's a big spike. That big spike occurs because, at least in the United States, the holiday shopping season is very important. And when the Christmas holidays roll around, stores will hire many, many temporary workers to help shoppers buy the Christmas gifts. And then when the holiday season is over, the store doesn't need those workers anymore, and then it'll lay them off, so they're now unemployed, and sometimes those workers will file for unemployment. So that's the source of a lot of the seasonal pattern there. So we can see that there's structure in this time series that you could use to maybe make a prediction of what it's going to do one step ahead, the next week's numbers. But we'd like to augment that we would like to augment the information we can get from looking at just the structure of this series by itself with an outside data source. Right? So what I want to do is I want to think about maybe what an outside data source might be that we could use to help us make an even better prediction than we could from just looking at the data on its own. And that outside data source that I'm going to focus on today is Google Trends. So the broad structure of what I want to talk about today is I first want to give you an introduction into Google Trends data. What is Google Trends and how can you use it? Then once we understand the Google Trends data, what I want to do is introduce you to the types of models that we want to use to describe the data. So now that we'll describe the time series data that we care about using a tool called Bayesian Structural Time Series Models, or BSTS is the name of the software package that we've developed to fit these models. And then in addition to the information in the time series, we want to build in the information from this outside source. We'll do that through a particular type of regression modeling. And we're going to use what's called spike and slab regression models to combine those two sources of information together. Once we understand the models, then I'll show you some examples. We'll come back and we'll take a look at the initial claims data set again, and we'll see another economic time series that's has somewhat similar features. And then once we're done with the examples, we're almost done, but I can't stop myself from showing you some other kind of recent and cool features that we've built into the BSTS software, because nowcasting isn't the only thing that you would want to do with time series models, and the BSTS software is just so useful. I sort of need to show a few of the neat things it can do. After that, we'll conclude, and I guess there's a pub we can all go to. So let me get right to it then. Okay, trends. What is Google Trends data? Google Trends is a publicly available data source that Google provides. You can find it by going to Google and searching for Google Trends. You can also go directly to trends.google.com. And it can answer such hot button questions as, what day of the week are most people interested in vodka? I know that's on the top of all your minds. To answer that question myself, I went to Google Trends and I typed in the search term vodka right here. And I got this little time series that you see on the bottom. And you can see there's a very strong weekly seasonal pattern. It seems like people are always interested in vodka on a pretty regular basis. And it turns out that this time series has a peak every Saturday. So every Saturday, the vodka drinkers come out, and they ask questions like, how much vodka should go in a martini? Give me recipes for vodka, that kind of vodka drinks. You can compare other time series to this time series if you want. And so here's what happens if you add another search term, hangover. And then you can sort of look down here and see the red line and how does it match up with the blue line. Well, it turns out Hangover also has a very strong weekly series, and it has a peak every Sunday. So there's definitely information there about the public interest in various topics. Interestingly enough, sometimes some of these search terms can be ambiguous, right? If I search for vodka, I guess that one's not really super ambiguous, but the search term hangover actually is ambiguous because hangover can be the thing that you have after you have too much vodka, but it could also be a very popular movie. There was 3 movies that were made, The Hangover, Hangover 2, and Hangover 3, and those are also things that people tend to search about. And so if you're worried that the search term you're looking at, the data that you're looking at doesn't match up with the idea that you're trying to learn about, you can restrict your Google Trends query to a particular category, right? So in this case, you might search for vodka under food and drink, and under food and drink, there might be beverages, and then under that there's alcoholic beverages, and then under that you find liquor, right? So these different categories that you can restrict yourself to are, there's a hierarchy of them, right? There's a lot of them, and they're sort of organized into a tree structure. Even more interesting is that you can actually go to Google Trends and you can select a category without selecting a search term first, right? So I could go into Google Trends without putting in a search term, and I can click on beverages, alcoholic beverages. And if I don't put a search term up there, then what I'll get from my little Trends time series is an index. So this is an overall summary of what fraction of Google searches were related to alcoholic beverages as a category, okay? And so that's kind of an interesting idea because that's probably going to be more indicative of the public's interest in alcoholic beverages than searches for any particular alcoholic beverages, right? Just like if you're trying to understand how the stock market moves, you can follow the movement of an individual stock, which is probably helpful, or you can follow the movement of a stock market index, like the Dow Jones or the NASDAQ or the S&P 500 or others, right? So when we think about these Google Trends search categories, I mentioned that there's a lot of them. They're organized in a hierarchy. If you take all of the top ones and all of the sub-levels and the sub-sub-sub-levels, if you look at all of them, then there's something like 630 or so of these different categories. And that's kind of like 630 different stock market indices, except that it's not stock market indices, it's public interest indices. So if you want to know how interested is the public in a particular category, you can look in Google Trends and see, well, how often do people search for that category? 600 or so public interest. Okay, that's what we just said. Now, if you are interested in individual search terms, then you can then there's another tool that you might be interested in, which is called Google Correlate, right? So Google Correlate is, if you want to see what else are people searching for when they're searching for, Britney Spears or something, you can go to Google Correlate, which you find by going to Google and typing Google Correlate. I forget the URL, but that's how I get there. And then you can type in a search term up here at the top of Google Correlate, and what it'll do is it'll give you other search terms that are correlated with it, right? In addition to seeing what other search terms are correlated to a particular term that you care about, you can also click on a little link next to the search box, and you can say, upload your own data, right? So if you have a time series and you want to see which Google search queries are most correlated with your time series, you can click on this little button. It'll say, tell me the file that contains the data that you're interested in, and then you can just upload that data into Google. So I did this over here on the left-hand side. I had a text file that had the initial claims for unemployment data series in it. I uploaded it into Google. It shows me the data as I'm uploading it in a little thing that sort of looks like a spreadsheet. It asked me things like, what country is this data for, and it sort of makes sure that I have the data in the format that it's expecting with dates that look like what it's expecting. But when I'm done, I can say search correlations, and that's how I get the picture over here on the right-hand side. So what you're seeing on the right-hand side isn't data that's correlated with a particular query that people type into Google. It's actually the Google search terms that are most highly correlated with the initial claims for unemployment series that we would like to be able to model. And the screen, unfortunately, is too small for you to be able to see what these things are, but you end up with, let's see, Michigan unemployment is the top answer. And Michigan unemployment is correlated with the initial claims time series with a correlation of 0.86, right? The second highest correlation is Idaho unemployment. And so a lot of these series that are coming back are kind of questions about the level of unemployment in the different states in the US. But after you get past all the states, you get to things like unemployment filing. Now, unemployment filing, and where is the unemployment office, and how do I file for unemployment? These are the types of questions that if you're currently unemployed and you've never been unemployed before, you don't know how to be unemployed. How do I go about going to the unemployment office and filing for unemployment insurance? I've never done it before. So what do? Well, you go ask Google how to do it, right? And so this is a particularly interesting category, and it's indicative of a particular type of distress that the population might be under. So some of these series are questions about sort of the general state of the economy, but some of them are desperate cries for help, and that you would sort of expect that sort of thing to be pretty strongly correlated with actual initial claims for unemployment. Okay. So that's a very brief introduction to Google Trends data and to Google Correlate data. They're both accessing the same underlying database of Google searches, but one of them is sort of focused on providing values for individual search terms or categories of search terms, and the other one is there to give you kind of a whole bunch of these things at once. So I should probably mention that once you have these data, you're not limited to the graphs that are shown on the screen. The Google Trends interface and the Google Correlate interface will both allow you to click a little button or a link, and you can download the data as a CSV file. And once you have the CSV file, you can upload it into whatever analysis software you'd like to use, and then you can do a full analysis with it. So the data is actually available to do kind of a proper statistical analysis. Okay. All right. So we have access to this Google data, and we can use it to maybe help us predict initial claims. How are we going to do it? Well, let me talk to you a little bit about the types of models that we think are useful for doing this type of thing. And again, we're going to focus on two different parts. This is one model, but it's sort of two pieces of model glued together. I first want to give you a very brief introduction to the time series part of the model, and then I'll give you a very brief introduction to the regression part of the model, and then we're going to stick these two things together into one overall model. Okay. Structural time series models look like this, right? There's a variable y that we're trying to describe the behavior of, right? So y is a number that evolves through time. And we have a mathematical model that says y is some function of a latent variable alpha sub t. So alpha, y is a scalar, yt is a scalar. It's 3.6, and alpha sub t is a vector, right? I'll show you in a second the stuff that the vector has in it, but for right now, just trust me, it's a vector. And then I'm going to take this vector and I'm going to add up some bits of the vector and with these coefficients z sub t. And then there's an error term, right? So basically what this equation says is that y is equal to a linear combination of some latent variable, some unobserved variable, plus some noise, okay? The noise happens to be normally distributed noise, and it's got a variance term h sub t. And you look at this equation and you realize, wait, there's no time series there. That's just y is state plus error, right? The time series part occurs down in this equation right here called the transition equation. This first one is called the observation equation. The second one is the transition equation. The transition equation is the part that tells you how the state at time t plus 1 evolved from the state at time t. Okay? The transition equation says that there's some matrix, capital T, that multiplies alpha t and takes it into alpha t plus 1. And to that kind of modified alpha t, we're going to add another bit of error. So this little eta sub t down here is another error term, just like the epsilon t was, but it's an error term applied to the state as opposed to the observed data. That error term has a variance matrix q sub t. And some of the models that we're going to use are going to we're going to be keeping track of little bits of state, and they're going to be modified deterministically from one time period to the next. And so there's going to be some of the state models that we like to use that the error term isn't going to be the same dimension as the state. And so I need a little matrix here that can take a two-dimensional error term and blow it up into a 50-dimensional state vector or something like that if the dimensions don't match up. That's where that thing comes from. Okay, if this is the first time you're seeing a model that looks like this, then it's a bunch of gibberish up here on the page, and if it just looks like a bunch of squiggles, that's okay. Let me draw a picture for you instead. So here's how we're going to build the state part of this model. What we're going to do is we're going to look at our time series, and we're going to say to ourselves, okay, it looks like this time series has a reasonably strong trend to it. And so what I'm going to do is I've got a drawer full of potential models I could use over here for describing trend. And that, when I look at that trend, that kind of looks like a local linear trend to me. So let me pull this local linear trend model component out of the drawer, and I'm going to make that the first component of my state, right? Now the local linear trend box that I'm going to pull out of the drawer, remember this model has all these Z's and T's and R's and things like that. There's going to be a little chunk of a Z and a T and an R in that local linear trend box. And I'm going to put them in the overall Z and T and R for the model. And then I'm going to look at my time series and I'll say, well, in addition to the trend, it also looks like it has a seasonal component. So I've got a few models down here that I could think about using for my seasonal component. I'm going to pick the one that I think is probably the most relevant, and then I'll pick out the Z and the T and the R from that box, and I'll put them, I'll stack the Z's on top of each other. I'll take the T's and I'll put them together as a block diagonal matrix. And you can sort of organize the models this way. They're very modular, right? You get to pick out, I think I need this bit, I think I need that bit, I think I need that bit, and you can sort of put the different bits of the model together that you think are appropriate for the problem. So it's in this sense that these models are structural time series models. You're looking at the structure of the data and you're trying to build a model that has a similar structure so that you can describe it, okay? Now, when you actually write down the form of these models mathematically, it looks something a little bit more like this, right? We looked at that time series earlier and we said, okay, I think I can see a trend, right? I can see that the big hump where the financial crisis happened, right? So I've got a bit that I can call the trend. Let's call our trend mu t. Mu is a letter we use for means a lot of the time, so that's a good letter to use for trend. There's a seasonal component as well. And then there's a regression component that I can add on to it at the end, right? Now, okay, so this is my observation equation. Y is equal to, I've got a mu and a gamma and a beta transpose x. These are all part of my state vector. And by adding this component and that component and that component together, that's what the Z does. Z is the thing that sort of picks off those components of the state. And then here's my error term. Now, my state equation is down here, right? So this particular model that I chose to use to describe the trend is something called the local linear trend model. It's a pretty well-known one. And what this model says is that the value of the trend today is equal to the value of the trend yesterday plus a little bump plus an error term. Okay? And if you look at it, if you squint at this model just right, that little bump sort of looks like a slope of a line. Right? You have to look at it just right. So that normally when you think about a linear equation, right, normally the slope term of a linear equation is multiplying a variable, right? Well, this thing is actually multiplying a delta t, right? It's just we're in a discrete time model, and so that delta t is always 1, right? So what we have is our trend today is equal to our trend yesterday plus, maybe instead of a bump, maybe I should call that a drift or a slope. And so this is sort of, well, let me just call it the slope term. And the slope term is a random walk. The slope term today is whatever the slope of the line was yesterday plus an error term. Okay? So my trend is actually using up 2 dimensions of my state, one of which doesn't contribute to y directly. It only contributes to y in the sense that the slope is going to make the trend either bigger or smaller in the next time period. Well, I also have a seasonal component to this model, right? And if you think about seasonality, well, if you were in a freshman stats class and you had to model seasonality, then one way that you might choose to do it is you might think, well, you know, what if so I've got, 12 months or, winter, spring, summer, fall, or whatever the right notion of seasonality is. And you might think about putting dummy variables down there for seasonality. Maybe I've got a dummy variable for January and a dummy variable for February, and just indicator variables for which season you're in or month you're in. And I guess if you're going to have dummy variables for winter and spring and summer and fall, if you're going to go with the 4 seasons here, well, from your regression modeling class, you can't have all 4 dummy variables, right? You're going to have to leave one out because there's going to be a perfect collinearity in your model. I guess you could also think about other constraints than just leaving out one of the dummy variables. You could maybe constrain the sum of the coefficients of all those dummy variables to add up to 0 or something like that. You need some sort of a constraint like that in order to make the model go. Well, what this gamma thing is I've got think about the gamma as a kind of a regression coefficient for your seasonal dummy variables. That's almost exactly what it is. And in order to make this thing kind of act like a regression coefficient, I need to impose some kind of a constraint. And the constraint that I'm going to impose is that I want the sum of all my seasonal components over the course of an entire cycle, right? All over a winter and a spring and a summer and a fall, I want those coefficients to add up to 0. And what we're going to do here is we're going to make these coefficients add up to 0 in expectation. Well, if that's true, and I'm going into winter right now, I'm trying to figure out what's my gamma going to be for winter. What I need to do is I need to take the gamma for fall and spring and summer, right? And I'll look at those things, I'll add them up, and I'll put a minus sign in front of them, and that's going to be the mean for my winter coefficient. Because if that's my mean, then in expectation over the course of all 4, these things are going to add up to 0. So that's what this expression says down here. That's my seasonal effect. All right. So if that was a lot to take in, then then that's okay. It's going to get easier from here. But if you're interested in these types of models, then there's a sort of a big library of these kind of state components that you could use to fit different types of time series. The software package that we developed in order to solve this nowcasting problem has been released into the public domain. It's part of R. I don't know. I imagine a lot of you guys are R people. And so it's the name of the package is called BSTS. And the way that the BSTS software works is sort of the same way as kind of the math works when we're describing these models. When you think about one of these models mathematically, you say, well, okay, let me think about defining what my state looks like. I've got a trend component, I've got a seasonal component, and then once I've defined the thing, I can fit the model. Well, the same thing works in software. So the way you fit one of these models in the BSTS software package is first you have to build a state specification. What does my state variable mean? What does it have in it? Well, you can start off with an empty state, and you can add a local linear trend model. Right? That's one of the things you have in your drawer that you can just sort of pull out. And when you add your local linear trend to an empty state, you'll end up with this guy right here. If you want to take this state specification and add a seasonal component to it, well, you just call the add seasonal function, and you'll add the seasonal to the state specification. You tell it you have 7 seasons if you have 7 days of the week or something like that. And then once you have your state specification specified, you can just call the BSTS function in R, and you give it the formula for the linear equation that you want to fit. Here's the state specification. It's a Bayesian algorithm, so you have to tell it how many iterations of MCMC you want to run. Tell it what your data is, and you're off and running. Okay, all right. So we've defined the model. I've shown you how to punch the buttons on the computer in order to fit the model. Under the covers, I want to tell you a little bit about how the model is getting fit. Right. So it's a Bayesian model, and so instead of climbing to a lot of statisticians and a lot of machine learning people, when they think about fitting models, they imagine some sort of an optimization problem where there's a function to be optimized, and I'm going to climb to the top of the hill, and whatever values I get at the top of the hill, that's going to define my model. In a Bayesian setting, you don't think about things that way. You think about building a large ensemble of models. And near the top of the hill, the values near the top of the hill, you're going to have a lot of values in your ensemble that are near those guys. And as you move farther and farther away from the top of the hill, then you'll end up with a smaller and smaller number of models in your ensemble. So the thing that defines a model for us here is the set of variance parameters. So we had a variance parameter from the observation equation. We have some variance parameters from the, where are these guys? So here's an error term, he needs a variance. Here's an error term, he needs a variance. Here's an error term, he needs a variance. So we have all these different error terms, they all need their variances. And then I've got my regression coefficients, beta, I'm going to have to draw them as well. So these are parameters in the model, and I need to learn their values. The thing I really care about in the model is the state vector, right? The state vector is the value of the trend and the value of the seasonal. I need to know those values too. We don't call them parameters, they're unknowns, latent variables, but those are things we need to learn as well. And the way that we're going to go about learning these things is we're going to assume that we know the model parameters temporarily, and use Bayesian statistics to take a draw of the state from its posterior distribution. So given the parameters and given the data, there's a probability distribution for the state. I'll take a random draw from that distribution. And then I'll assume I know what the state is, but I don't know what the parameters are. And given the state values and given the data, I'll be able to take a draw of the parameters from their posterior distribution. And I can just alternate back and forth. I can draw the alphas given the parameters. I can draw the parameters given the alphas. Okay, this is a very well-known algorithm. It's a Gibbs sampler, if that's a term that's familiar to you. One half of this computation turns out to be a lot harder than the other half. So it turns out that if I knew what the state was, then drawing the parameters from their Bayesian posterior distribution is really, really, really easy, right? All of these different model components wind up being some sort of, a random walk with a funny kind of drift term. And so if I can just kind of take the appropriate differences of all these random walks, I can transform the state into white noise, essentially. And the only thing I need to learn is the variance of that white noise. And that turns out to be a super easy problem. It's a little bit more, some more sophisticated techniques are needed in order to actually draw the state given the parameters in the first place. And there's some references that if you're interested in these types of models, that I'd like to encourage you to follow up on. These are algorithms that were developed in the kind of mid-90s by papers by Carter and Cohn and Sylvia Furber-Schnatter, improved a year later by De Jong and Shepard, and then we get into the 2000s with a method by Durbin and Koopman. I don't want to get into the details of how these methods work, but suffice it to say, what they allow you to do is to take a draw of these serially correlated state variables given the data. Okay, and then once we have the data, we can take a draw of the once we have that draw, the other draw is easy, and then we'll kind of alternate back and forth between simulating both of these things from their distributions. Okay. So that's the time series bit, right? That's my description of the Bayesian structural time series models. What I want to do next is I want to talk about spike and slab regression, right? Spike and slab regression is an example of a sparse regression, right? So a regression model is sparse if you have a whole bunch of X's, right? For us, we're going to have a whole bunch of different Google search terms that we might think about using as predictors for our time series model. And if you have a whole lot of X's, if you have just a bunch of them, then odds are you really don't need all of them, right? So in a sparse regression or a sparse model, the word sparse means that a lot of the coefficients in that model are zero. Okay? Now, I want to compare this, the spike and slab regression that I'm going to introduce you to on the next slide with a different, probably a more well-known type of procedure that's used for sparse regression modeling called the lasso. Right? The lasso, what it does is it takes the normal optimization criterion that you use for regression models, which is fitting the regression using least squares and minimizing the sum of squared errors, and it adds a little penalty term to that optimization criterion. And the penalty term takes the absolute values of the coefficients and it just adds up the absolute values, and then there's a little knob right here that you can turn this way or that way, and that'll control kind of how big or small a penalty you're adding. And from one point of view, the lasso is a method of producing sparse regressions. So I have a little illustration of what sparsity looks like in the lasso setting. So if we think about the optimization criteria for regression as least squares, and then we think about a penalty term being added to that, well, if you exponentiate all that, then the optimization criterion turns out to be the likelihood function for your regression model, and the penalty term sort of looks like a prior. And in particular, it looks like a double exponential prior. If you take the absolute value, e to the minus absolute value, then you end up with something that sort of looks like an exponential distribution fading off in 2 dimensions. So we can imagine this little dotted line right here in the left-hand side of or in the left panel as being the likelihood function for our data. And here's our double exponential distribution, the dotted blue line, right? And, of course, what Bayesian inference tells you to do is to take your likelihood function times your prior, and that gives you your posterior distribution. And so in this case, our posterior distribution is the solid black line. And you can see that, if you were to climb to the top of that posterior distribution and choose your one favorite value for the parameter we're trying to estimate, the mode of that distribution occurs at 0. Okay? And so if our goal in life was to estimate regression coefficients using their posterior mode, then this lasso prior would be something that would produce modal values of 0. But of course, what we're going to do in a real Bayesian analysis, instead of just a point estimate analysis, is not just try to find a single model. What we're going to try and do is make a big ensemble of models, right? Well, and if we were to sample a large ensemble of models from this distribution, we might get a lot of them that are kind of near 0, but none of them would actually be 0, right? So in this picture, what you have is a notion of sparsity where the most likely value is 0, but none of the actual values that this distribution describes are actually 0. So it's non-sparse in that sense. Over here on the right-hand side, incidentally, I've got exactly the same picture, but I've got a kind of a taller, skinnier likelihood that's supposed to represent more information in the data. And you can see that if you have more information in the data, then your mode might be something other than 0. Okay, so I want an alternative to this usual notion of sparse regression modeling, and I want to build an alternative that will allow me to actually have posterior mass at 0 when I do my posterior simulations. Why would I want to do that? Well, I kind of think that if I have, a very large number of predictors in my regression model, it's kind of foolish of me to try and find just a single model that identifies which predictors are in and which predictors are out, right? There's a really good chance if I do that, I'm going to get it wrong. And if you think about it this way, so let's imagine that if I have 100 predictors that are available and I have to decide which one is in or out, right? Well, if you think about how many models that corresponds to, well, if there's 100 predictors, that corresponds to 2 to the 100th models. And we know that's a big number, but let's stop and think just how big that is, right? So if I've got 2 to the 100th models, then I'm not really good at thinking in base 2. I'm better at thinking in base 10. So if I take, 2 to the 3 is approximately 10, but let me sort of fudge the 100 a little bit. So 2 to the 100 is, let's call that maybe 10 to the 30, all right? Okay, so that's a 1 with 30 zeros after it. How big is that? Well, Avogadro's number is 6 times 10 to the 23rd. I had to go back and look on Wikipedia. It's been a long time since I took chemistry to remember what Avogadro's number is, but what it does is it tells you the number of atoms in a mole, I guess. And so I guess if each of these models was an atom, then our whole model space would have 1.6 million moles of mass. What does that mean? Well, if we think about carbon, I guess, is the easiest element to talk about this stuff in. And so a mole of carbon was 12 grams, turns out. You can learn all kinds of stuff on Wikipedia. So if I have this many moles of carbon, then my space of models, each model is an atom, ends up weighing 20,000 kilograms, which means something to you guys, you Europeans. To me, I think about it as 22 US tons, right? That's a pretty big block of carbon. I don't know how big a space in this room that would take up, but I imagine it's substantial, right? And what we're trying to do, I guess, in this model right here is find the best of all those atoms out of that 22 ton block of carbon. That seems like it's a tall order, right? I'm probably going to get that one wrong, okay? Now, the problem isn't quite as bleak as I just made it out to be, because when we're trying to figure out which variables should go in our regression model and which variables should be left out of our regression model, it turns out that there's not all of them are kind of equally hard. There's going to be some variables that are so obviously helpful that, yeah, okay, any selection criterion will include them, and there's going to be some that are so obviously garbage that they should be left out. So if I have 100 predictor variables, I probably don't have 100 equally hard decisions. There's probably 2 or 5 or 10 or 12 variables that I'm not sure about, right? But even if there's 12 variables I'm not sure about, or 10 variables I'm not sure about, that's 1,000 models that I should probably be averaging over to improve over my predictions were I to choose the wrong model. Okay. All right, so what am I going to do instead of the lasso idea? Well, what I'm going to do instead is I'm going to imagine that each variable can be in the model or out of the model with some probability, right? And so maybe there's a coin with a certain probability, and the probability could be different maybe for every variable. That's going to determine whether it's in or it's out, okay? And so I'm going to take my vector of regression coefficients beta, and if we have 100 predictors, beta is a vector that has 100 things in it, and I'm going to make a parallel vector to that, and I'm going to call that gamma. Now, gamma is a set of zeros and ones, the same length as beta. And what gamma equal to 1 means is that beta in that position is in the model with a non-zero coefficient. That variable is in the model. That's what that means. Okay. And now what I'm going to do is I'm going to take my prior distribution for my regression coefficients. In a regression model, you've got a set of regression coefficients and you've got a residual variance term. I'm going to factor my model, P of beta and gamma and 1 over sigma squared. I'm going to factor it this way. I'm going to write a distribution for beta sub gamma. And what I mean by this little subscript here is this is the subset of the betas that have non-zero values. I'm going to write this a distribution for this guy conditional on gamma, right? So here I get to for this little subcomponent of my distribution, I get to know which values of gamma are in and out, and sigma squared. I'll write P of sigma squared given gamma and then P of gamma. Right? So I've got 3 different distributions I need to specify in order to specify my prior. The distribution over gamma is what we call the spike part. This is a spike in slab regression. So this is a spike, and we think about it as a spike because what it's doing is it's essentially putting a point mass at 0, right? Every coefficient has a certain prior probability of being left out of the model, right, or being included in the model. And this spike equation that I put here is just the product of Bernoulli distribution. So this is literally just me thinking about a coin with a probability pi sub j, the variable is going to be included, and with 1 minus pi sub j, the variable is going to be excluded. Right? So what's the slab? Well, the slab is essentially a standard conjugate normal prior. And if that, I don't know if that sequence of words meant anything to you, but the slab is essentially the prior distribution that I would use if you were to come and tell me which of the components in the regression model were actually the important ones, right? In order for me to specify a mathematically convenient version of this slab prior, I'm going to need to have a vector b, which is my prior guess at each of the regression coefficients. And what I'll do is I'll just take, once you come and tell me which ones are in and out when I condition on gamma, I'll just take a subset of that b and use it for this part of the model. And then I've got this kind of funny thing where I'm inverting a matrix twice over here. It's because what I really want to do is I want to think about this normal mean variance thing, but I want to think about the information in this prior on the precision scale. The precision is the inverse of the variance. And so what I'll do is I'll take the precision matrix that I would use for my prior distribution, and I'll take the rows and the columns of that precision matrix that correspond to the gammas that are included. Okay? So I've got a lot of, if I'm going to be a Bayesian, I'm going to specify a prior for this problem. There's a lot of numbers that you need to specify, or I need to specify, in order to actually turn all these equations into something that you can implement on a computer. We need to specify this B vector right here. Here's a matrix that has a whole bunch of stuff in it. This omega matrix has a bunch of stuff in it, and I need to specify all these pi's. And so if I'm going to be writing software for people to use to solve these types of problems, I need to kind of make it easier on my users. So here's what I'm going to do. In order to specify the pi's, I think it's going to be hard for people to say what prior inclusion probability should be for each one of these variables. So what I'm going to do is I'm going to ask people, how big a model do you kind of expect to see? Right? What's your expected model size? And so if you have 1,000 predictor variables that are potentially in the model, and your expected model size is 4, then what I'll do is I'll take those prior inclusion probabilities and I'll say, oh, I've got 4 over 1,000, everyone 0.004 is your prior inclusion probability. Okay, well we just dispensed with a whole bunch of values that we can specify just by asking a single number. B equal to 0 is sort of a standard value, right? So we can kind of use 0 for that B vector. I got a funny looking thing here for my precision matrix, and so let me ask you to just assume that alpha is 1 for a moment, and we can ignore all this stuff over here on the other side, right? In your regression class, one of the things that you learn about a regression model is that the variance of your estimated regression coefficients is x transpose x. Okay, so that's sort of a fact. And what that means is that the precision of your estimated regression coefficients is x transpose x, right? So now, if the precision is x transpose x, that means the total amount of information that you have from your entire data set is x transpose x. And so then I'll take that total amount of information and I'll divide it by n, and that means that x transpose x over n is kind of an average amount of information that's present in an individual observation. I can then multiply that by this number kappa here, and so kappa is sort of like what's the how many observations worth of average information do you want to associate with this prior guess B? Right, that's what that means. So far I have to ask you two numbers. I have to ask you your expected model size, and I have to ask you for a number that's how many observations worth of information do you want to use to kind of shrink towards 0. So that's enough for me to specify both B and omega inverse, assuming we don't worry about this alpha thing. The next thing I need to do is I need to come up with a prior distribution for the residual variance in this model. And it's hard for people to think about variances in particular. It's going to be super hard for people to think about residual variances. But people that are used to kind of doing regression problems, they're used to looking at the regression output and saying, what was my R squared, right? Well, what I know is that in a regression, what R squared does is it's a mapping between the sample variance, the variation of y around the average y, and the residual variance, which is the variation in y around the regression line. And the formula is that your residual variance is 1 minus R squared times your sample variance. Okay? So I'm going to cheat and look at the data, and I'm going to assume that I know the sample variance. Right? I'm going to ask you, what's your expected R squared? Right, so if you give me an expected R squared, then that's going to give me a guess at the value of the residual variance. And then I'll ask you one more number, which is how many observations worth of data do you want that guessed away? Right? So I need to ask you 4 numbers in order to specify this prior. But you know what? There's kind of reasonable default values out there for all 4 of these 4 numbers. And so if you don't want to be bothered thinking about priors, you don't have to. Right? I can use a default value for the expected model size. I can use a default value for kappa and df and all that other stuff. I can say my expected R squared is 1/2. Okay. And so, if you're not uncomfortable with any of those values, then that's my prior. So let's use my prior, right? If you want to specify your own prior, you can, but you don't have to. Okay. So we have one more step to do in math land, and then we'll get back to the applied part of the talk. We need to be able to take that prior that we just specified and the likelihood of the data and turn that into something where we can actually take draws from the posterior distribution. And the thing that the quantity that we need to take draws for is this gamma thing. The reason that we only need gamma is that because we chose a conjugate prior for the regression coefficients and the residual variance, we can actually integrate them out of the probability distribution and just look at the marginal distribution of gamma. And this marginal distribution of gamma has a form that looks, you know, I don't know if it looks mean or scary or what, but you know, I've seen worse, right? It's a relatively clean expression. The expression has two variances here. It's got the prior precision of the regression coefficients in the numerator. It's got this V thing down here. What this is the posterior precision of the regression coefficients in the denominator. And you'll notice that both of these guys are subscripted by gamma, right? So here's a matrix that needs to be decomposed. Here's another matrix that needs to be decomposed in order to compute its determinant. But if I have 1,000 predictors, potential predictors in the model, but only 4 or 5 of them are included, then this is a 4 or 5 dimensional matrix, right? And I can take a determinant of a 4 or 5 dimensional matrix really, really easily. So it turns out that as long as my model really is sparse, this is a formula that I can evaluate with very little computational effort, right? Computationally, this is very, very fast. The other parts of this model include this P of gamma. So if I'm looking at gamma is what's in and what's out of the regression model. So if I'm looking at a model that's kind of a priori looks good, then that'll help the posterior. Kind of unsurprising. This other little thing down here, this SS, you can think about that as kind of like a sum of squared errors, right? So this is saying, does the model fit the data? So if the model fits the data really well, it's going to have a high posterior, and if it doesn't fit the data really well, it'll have a low posterior. So this is an expression that I can evaluate. You give me a gamma, I can evaluate this expression, and that's enough for me to do an MCMC sampler to sample this vector of zeros and ones. All I need to do is I need to pick a random location in this gamma, right? So location number 17, is beta 17, is it in the model, is X17 in the model or is it out of the model, right? Well, let's suppose it's in the model right now, right? I'm gonna take the rest of my gamma vector, it's gonna be whatever it is. I'm gonna flip the value from 1 to 0 in location number 17, right? So I'm gonna evaluate gamma with gamma 17 equal to 1. I'm going to evaluate gamma with gamma 17 equal to 0 with everything else fixed. And then I'll take these two numbers, I'll normalize them so that they add up to 1. And then those are going to give me the two probabilities that I care about, right? So I'll flip a coin, and if it comes up, that I want that gamma to be present, it'll be present. And then I'll repeat it for another position in gamma, right? So I can do this just kind of marching up and down the gamma vector in a deterministic order or random order, and that'll be an algorithm that will it's a valid MCMC algorithm for sampling gamma. And then later on, if I want to go back and take draws of beta and sigma, I can do that because I've got a conjugate prior. Okay. So that was, I don't know if that came across as extra heavy mathematical or not, but I sort of get the sense maybe it did. But anyway, that's for those of you that were able to follow that, that's what's going on under the hood in the model. So just to summarize what we said, we have two components of the model. We have a time series component, and we've got a regression component, right? And these components, they add together, right? My model is time series plus regression is equal to y, right? And the way that MCMC works is that, I can assume that I know what the regression component is, and I can do an MCMC draw of the time series stuff, right? And then I can assume I know what the time series is, and I can subtract that from y, and I can do an MCMC draw of the regression stuff, and I can just, kind of keep going back and forth in between those two components, right? And so that's how the MCMC algorithm works, and that gives me kind of posterior draws of all the model parameters and the state. All right. Okay. Let's get back to the data a little bit. So what I did was I took this initial claims for unemployment time series, and I said, let's try to model this thing as a local linear trend model, and let's include a seasonal component, because we saw a seasonal component in the data, and let me take the Google Trends data for the top 100 predictors that are most highly correlated with initial claims. I said, let's run this thing with a spike and slab regression with an expected model size equal to 3. I just picked the number 3 because it was my favorite number that day. Let's go ahead and do my MCMC, and let me look at the posterior probability that each of my predictor variables shows up in the model with a non-zero coefficient. Right? Everything started off with the same prior probability of being in the model, but let's look at the posterior probability after I do the updates and control for the time series stuff. Well, there's two predictors that show up with very high probability in this model. What we're looking at here is the length of the bar is the probability of inclusion conditional on the data, and the color of the bar is the probability of having a positive value if you're included. So if you saw a black bar here, that's going to tell you it's a negative coefficient. If you see a white bar, it tells you it's a positive coefficient. If you see something that's sort of light gray, then that's sometimes positive and sometimes negative. Well, the number one most important predictor in this model winds up being unemployment office, right? Which is sort of that makes a lot of sense, right? If you're unemployed, you don't know how to you don't know how to be unemployed and file for unemployment insurance. That's the type of query that someone might type into Google. The second most important query winds up being filing for unemployment, right? The third one, you'll recall that out of our big list of Google Trends variables or correlate variables, there are a lot of different state unemployment. Michigan unemployment, Idaho unemployment. Well, it turns out that this model thinks Idaho is the most predictive of all those state-level unemployment queries. And so Idaho shows up in the model about half the time. It's got about a 50% probability of being in the model with a non-zero coefficient. All right. And then below that, we end up with a couple other search queries that are probably spurious. These are probably not kind of economically meaningful variables. Sirius Internet Radio and Sirius Internet. For those of you that don't know, Sirius is a satellite radio company, and it just so happens around the time of the financial crisis, they're getting out of the, not necessarily out of the satellite radio business, but they're trying to expand into internet radio. So they happen to be in the right place in the right time, but not necessarily related to the unemployment phenomenon. If you're curious about what do these predictors look like, you can look at the, and by the way, there's a number, this posterior inclusion probability. I could show this for all 100 variables, but it gets hard to see individual ones, so I'm only showing the ones that have inclusion probabilities bigger than 0.1. That's what this inc equal to 0.1 means. You might be curious about what the other predictors look, or what the chosen predictors look like. And so I can make a little time series plot of the predictors. So that the solid blue line is the initial claims for unemployment series. It's been standardized to be on the same scale as everything else. And then there's a dotted line here for filing for unemployment. There's a slightly smaller dotted line for Idaho unemployment. There's a solid line for unemployment office. And you can see that they all kind of track the Sirius Internet Radio series pretty closely. But of course, you'll remember these are data that came from Google Correlate, right? They were chosen because they had a really strong correlation with the series. And so I guess this is probably not a big surprise. All right. You might ask the question, well, how much I've got a model that has several components to it. It's got a trend component and a seasonal component and a regression component. How important was each component? I mean, how much explaining of the variation in my time series did each component do? Well, I can look at the posterior distribution of the trend component and the seasonal component and the regression component and kind of see how big they are. I've got a little fuzzy line that's plotted here. It's not the projector's fault. It's not your eye's fault. This is an actual fuzzy line. And what it's trying to do is it's drawing a straight black line at the posterior median and sort of stepping off like to the 51st percentile and 49th percentile and drawing a polygon that's slightly less black, and then you sort of take percentile steps away from the median, and you keep drawing polygons that are lighter and lighter and lighter shades of gray, and actually when you get all the way down to the first percentile and 99th percentile, it sort of fades off until you can't see it against the white background anymore. So this is a way to represent at each point in time what the posterior distribution looks like. That's why it looks fuzzy. So you can sort of see what the trend component looks like, and you can see what the seasonal component looks like. You can see that there's a little bit of variation in the seasonal component. So, if we had done the intro stats thing of just using kind of straight, dummy variables for the months, then we wouldn't have captured this evolving seasonal trend. And you can see what the regression component looks like. And so it looks like what the model is doing is it's trying to fit the sort of general pattern of the data with the trend, but the data contains this big catastrophe, which is the housing crisis and financial crisis, and It's using the regression to sort of capture the big shock. You could ask the question, does it help? Does including the Google Correlate data actually help you do a better job of describing the data than just a simple time series model alone that didn't use the Google Trends data? And what we can do here is we can actually fit two different models. One of the models is going to be the model I just showed you. The other one will be exactly the same model, but I'm not going to include a regression component. Right? And for each one of those models, we can imagine computing the probability of tomorrow's value of y, initial claims, given all the conditional value of, given all the initial claims data up until today. Right? So you can imagine what the one-step ahead prediction errors might be in this model. And we can keep track of the cumulative total absolute one-step ahead errors. So these models are accumulating error. All models are going to make errors, right? And so the question is, how rapidly do the models accumulate errors? Well, the model that includes that does not include the Google Trends data, you can sort of see that it's kind of parallel to the model that does. In the early part of the data, these things are accumulating error at roughly the same rate. But there's a little spot right here where it kind of gets in trouble, and that spot winds up being exactly right above where the financial crisis happened in the data. So if we include the Google Trends, as you might expect from the previous plot that we just saw, we're using the regression component to try and explain away the big catastrophe that occurs in the middle of the data. Well, the model that includes Google Trends, it sort of keeps accumulating error at a more or less constant rate throughout the entire series. Okay. Let me show you one more example. So this is a second bit of economic data in which the financial crisis shows up very, very strongly. This is retail sales excluding food services, and this data is a little bit different than the previous data set because it's been deseasonalized. Right? So before we got this data from the Federal Reserve Economic Database, the Fed had already sucked out the seasonal pattern from the data, right? So we're not going to see that same sort of annual cycle that we saw in initial claims. The other thing that's different about this data set is that it's monthly, whereas the initial claims data set was weekly, right? And because it's monthly, what that means is I have many fewer observations. Right? So I guess this goes from 2004 up into 2013. So I've got 9 years of data. I've got 12 months per year. So I've got somewhere on the order of roughly 100 observations here. So I've got less data. I'm also going to use an additional data source. Right? So when I did the initial claims data, I just used the data from Google Correlate. Here, I'm also going to use the Google category data, right? We had those 630 categories we could have used from Google Trends, and I didn't use them before, but I want to use them now. And I actually want to use, I want to think about a couple of different subsets of the data that I could use. I could use everything, right? My Google Correlate data plus my 600 some odd Google category data. But I happen to have the chief economist at Google sitting over here as my co-author. And he can kind of use his subject matter domain knowledge to help pick out the Google categories that are probably going to be more economically relevant. So we have a HAL variant approved subset of the Google category data that we could use, and that's what's called econ here. And then I could just not use the category data. I could just use the 100 predictors from Google Trends, or I could use none of it. Separately, the fact that the data was deseasonalized before it came to us led to a little debate. Should we then go and ourselves deseasonalize the Google Trends data before we stick it into the model, right? So we have several different models that we fit. Some of them have deseasonalized data, some don't. Some use the full subset, some use the HAL subset, some use just the correlate data, some use nothing. Well, the model that's just the local linear trend model, the pure time series model, you can sort of see how it starts to accumulate error. And at the point where the economy goes off the cliff, this thing, the model that's pure time series, it starts accumulating error at a pretty serious rate. So these models that are based on Gaussian processes, they tend to assume that when the data evolves, it's going to evolve in a smooth pattern. And well, here's a data set that evolves according to a very jarring pattern. It takes the model a while to adapt to that. Now here's a couple of other models. These are the two models that use the data from Google Correlate. It's the 100 individual search terms from Google Correlate. And yeah, you can see that they do better than the model that's just based on pure time series. And then there's all these other models down here, and they're kind of all doing, some are slightly better than the others, but they're all kind of about the same, right? So that using the full data set is just about the same thing as using the HAL variant approved data set. And then in each case, deseasonalizing the data before we fit the thing ends up working a little bit better. That's what you see here. So for the next few slides, I'm going to show you what the results from the HAL variant approved deseasonalized data set. What does the trend component look like, and what does the regression component look like? Well, the trend component sort of looks like this smooth trend here. Yeah, there's a downward bump, but it's sort of smooth. I don't know if it shows up well on the slide here, but there's a lot more kind of a gray fuzz around this line than there was around the previous example. And the reason that there's a lot more gray fuzz is there's a lot more uncertainty in the model that I'm fitting, right? I've got many fewer data points, and so I've got uncertainty because I've got a smaller n. And I've got many more predictors, and so there's more uncertainty because there's more ways for me to put all these predictors together. And so when you see that kind of the more uncertainty in the data here, that's why. Come over here and look at the regression model. What does it look like? Well, it kind of looks like a step function, doesn't it? Right? And I suppose that makes sense if we go back and we think about the original data, right? Because if we look at what does this data look like? Well, it sort of looks like it's up and to the right, and then a catastrophe happens, and then it's up and to the right again, right? So if we didn't have that big catastrophe, if we didn't have the financial crisis, this would be a pretty easy series to predict, right? Up and to the right pretty constantly. So that seems to be what the regression is trying to do. It's trying to capture that big fall in the series. What are the variables that showed up as important in the regression? Well, I've got a much smaller sample size. I've got a much larger number of predictors in the model, so I don't have that same stark. I've got here, here's the answer and here's not the answer. There's a little bit more uncertainty about what shows up. But if we look at the top two predictors, the ones that start with X's, by the way, these are the categories. Right? So the Google categories are showing up at the top of this list. The first one that shows up is real estate and home financing, which makes a ton of sense, right? Because the financial crisis was a housing crisis. That was what kind of led off the whole thing. The second one is society, social services, welfare, and unemployment. Okay, that's entirely justifiable. Third one, I don't know, is starting to be a little bit more of a stretch. I don't know if this one is actually, you can tell a story about anything, and entertainment, movies, movie rentals, sales, okay, people that would have gone out and maybe, gone out on the town or staying in and watching movies instead, I don't know, okay? But at least, the first two variables that show up here wind up being two of the more plausibly believable values. And they show up with the expected coefficient, right? So sales are going to go down as we end up with more kind of queries about, oh my God, how do I refinance my mortgage? Interestingly enough, one of the variables that doesn't show up very strongly in this list is automotive. So in the housing crisis, one of the things that happened, or in the financial crisis, one of the things that happened was the credit markets seized up, and the U.S. auto industry was caught in this credit crunch, and it was about to collapse. So the government had to kind of step in and bail out the auto industry. Well, one of the things that we noticed here when we went looking for it, it didn't show up in this plot, but when we went looking for it, there's actually 24 different automotive categories, and they're things like different brands, like Chevy and Honda and that kind of stuff. And if we look across all of those different automotive verticals, the collection of all 24 of these things, there's a 60% chance there's at least one of those guys in the model, right? I don't know how to algorithmically put that in a plot like this, but if I know that there's something to look for, then I can go looking for it. And I saw that there's at least a 61% chance that there's at least one automotive category present in this regression model. And that's kind of reassuring, right? Because if you're fitting spike and slab regression and you're not sure which of these 24 variables ought to be present, well, you'd like to, if you have two variables and they can't both be in the model, you'd like for one of them to be in the model half the time and then the other one to be in the model half the time, Well, here we've got 24 variables, and so I guess you'd like each one to be present kind of like 4% of the time or something, right? So with a 61% inclusion rate, we probably have a roughly 2% average inclusion rate for each of these 24, but collectively they wind up being important. You can look at the relationship between the series we're trying to model and the two most highly important predictors. And they don't look anything at all like the last plot I showed you, right, where the variables all came from Google Correlate, right? So, given that this series looks nothing like that series, why does it show up as so important? Well, remember that, the important thing in a regression model isn't necessarily your correlation with the variable you're trying to explain, but your ability to explain the stuff that the other stuff in the model hasn't already explained, right? Well, the important thing in a regression model isn't necessarily your correlations, but your partial correlations, right? And the interesting thing in this, when you look at this series, this retail sales series, is that we're up and to the right, and we've got a trend component of the model that can explain that bit, right? And then we have a huge catastrophe, right? And then we're up and to the right again. So really what we need is predictor variables that have big shocks right here at the right point in time. That's what the regression model is looking for in the variable selection step. And it just so happens these two guys, retail sales and social services, welfare, et cetera, they have a big movement in them at exactly the right time. There's other variables out there that also have big shocks at exactly the right time, and some of them are kind of fun. So one of the reasons that we decided to go with, in the paper, with the HAL variant approved subset of variables as opposed to the entire subset of variables is that if we use the entire subset of variables, all 630 categories, the one that the model loves more than anything else is searches for science and scientific equipment, right? Now that's weird. Science and scientific equipment. Why would that happen? Maybe, gosh, I just lost my job. This would be a good time to go back to school. Maybe I'll go study science. It's actually nothing to do with that at all. This little blip right here happened to be exactly the month that the Large Hadron Collider went online at CERN. And for those of you that were around back then and remember the news stories, you remember that this was supposed to be something that had some small probability of creating a bunch of black holes that were going to destroy the Earth. And that raised some concern among a certain fraction of the population. So what these are, this big spike in searches happens to be searches for, when are we going to die because the black holes are coming. So that's an example of a spurious variable, and you can sort of look at this and with your human intelligence tell that that's clearly not something that's going to be related to the process that we're modeling. And my little snip about this is artificial intelligence, as good as it is no substitute for the real thing. So with any procedure that is going to automatically select variables for you, there's some chance it's going to select a spurious one, and this is an example of a spurious variable. Okay, that's the end of what I want to tell you guys about nowcasting. Right. So what I want to do in just sort of a concluding segment of the talk is talk a little bit more about the BSTS software that we developed in order to do the nowcasting problem, but maybe focus on some other interesting stuff that it can do, right? I mentioned that we've got this big drawer of all these different trend components and seasonal components and things like that. And so we have components that will fit autoregressive processes for you. We've got a thing called a local level model, which is not quite as volatile as the local linear trend model. We've got a couple of different versions of local linear trend. And these are all different things that would be useful in different types of forecasting problems, or if you saw a time series that looked kind of, different than the ones I've shown you in a couple of interesting ways. We have a couple of different types of seasonal models that you can add. Holidays are kind of interesting when you get really deep into the business of time series modeling, because something funny happened here. that was Easter, right? Well, you got to figure out when Easter is every year and put in some sort of effect to model it, right? So we have the at least the U.S. holidays programmed up into BSTS, and we've got some code there to allow you to add other holidays. Holidays are kind of interesting because some holidays are holidays that always happen on a Thursday, right? Some holidays are holidays that happen the same month, the same date of month every year. Some happen, the third Friday in November, right? So there's a whole bunch of different ways that we keep holidays happening, and so we've tried to keep a couple of different holiday models in play for you to add holidays to your series. And then there's a different kind of regression model that I don't want to go into, but it's well known in some of the time series book, a dynamic linear model. You can add that as well. There's all kinds of diagnostics that you can get out of a BSTS model. Once you fit the model and you want to take a look at different aspects of it, then there's more different diagnostics that I'm going to be able to show you. But when you feed the model into the plot function in R, there's an extra argument that wasn't being used for anything else. And so what I did is I said, let's make that argument a string, and if you want this thing, you can plot it, and if you want that thing, you can just call it from the plot function. And I made sure to make one of the legal values of the string help. So if you want to figure out help me, what can I plot? You can type it there. Not the nowcasting examples that I gave to you were essentially short-term forecasting, right? I want to be able to forecast essentially one step ahead in my time series, right? I haven't seen the Y that's already been developed, but I've seen the X that goes along with that Y, so I'm able to use a regression component for that. Some people that study time series are interested in longer term forecasting, and so I mentioned that there's a couple of different types of trend models that you can use here, and the local linear trend model I described is really good for doing short term forecasts, but it's not so good at doing long term forecasts. So let me sort of explain why here. Let's suppose that I was interested in forecasting the future value of the Google stock price, which it turns out I am very interested in. So here's the historical value of the Google stock price. We had a stock split at some point. I've had to adjust for that, but adjusting for that, here's the historical value of the Google stock price. And you can look at this thing and you sort of say, well, what's the basic trend in the data? Well, up and to the right, and let's hope that continues. All right, so that's kind of what the basic trend looks like. So if I were to take the trend model that we used previously, the local linear trend model, I'll just remind you what it says. It says that Y is mu plus noise. Today's mu is yesterday's mu plus the drift term plus noise, and the drift term is yesterday's drift plus the drift term is a random walk. Okay. Well, a funny thing about random walks is that there was called a non-stationary process, right? If I try to imagine what the value of a random walk is going to be far into the future, I get more and more and more uncertain as time goes on, right? There's another type of time series model that's very common called an AR1 process. AR stands for autoregressive. It's a regression of the time series on itself, right? So if I'm concerned that this random walk thing might be a little bit too volatile for modeling the time series that I care about, I might think about replacing the model for the drift term or the slope term in my local linear trend, replace the random walk assumption on it with something that's more of an autoregressive process. So here what I can do is I can assume that there's a value D, that's sort of a long-run average value of the slope of the thing I'm trying to model. And I might have deviations from D, right? I might have a delta T minus D that's not, that deviates from 0. But I can imagine that there's an AR1 process. So this delta T minus D gets multiplied by a number here, rho, that is smaller than 1 in absolute value. That'll tend to sort of damp things down closer to D. And this AR1 process is stationary, right? What stationary means is when I think about what's going to happen to this thing over the course of a long period of time, it might kind of funnel out, but eventually it's going to turn level, right? It's not going to funnel out forever. It's going to sort of funnel out, asymptote, and then sort of stay level. All right. So in the absence of more cleverness on my part, I ran out of good names to kind of name this thing. This thing has an established name. It's a local linear trend. This thing right here, I just called it the generalized local linear trend, which I apologize for, but I couldn't think of a better name. So there's the code you use in order to do what I'm about to show you. So I fit the local linear trend model to the Google stock price, and then I imagined projecting the forecast distribution from this thing out for let's say, the next 6 months, right? And I ended up with this distribution right here. I want you to look at the scale of this plot, which goes from minus 5,000 to 5,000, and then there's beyond that, right? Let's go back and look at the original data, which is between maybe 80 or 100 or something way back at the dawn of time, up to maybe 800 right now. And that's over the course of 10 or so years, right? We haven't had a movement of 5,000 in the Google stock price at any point during those last 10 years, right? So when I look at the forecast distribution from this local linear trend model, and I see, well, okay, look, I'm getting numbers like 5,000 and minus 5,000. I'll be really happy if the stock goes to 5,000, but I'm sort of pessimistic that that's going to happen, right? I think this is a consequence of me trying to do forecasting with a model that's just too flexible. Right? In stats, we sometimes talk about the bias variance trade-off in some of these models. And if you end up with a model that's super duper flexible, then it's going to be able to track the data really well, but it's also going to have a big variance that's associated with it. And that's the world that we're in here. So I'd like to be able to assume a little bit more structure on this forecast distribution. And so what I did is I said, well, let's replace the random walk assumption of the slope part of this local linear trend with an AR1 assumption, a stationary assumption. And now when I forecast about 6 months out, I end up with a set of confidence bounds that, let's see, it might go down to, what is that, 600? It's at 800 right now. I'd be kind of bummed if it went down to 600, but that's within the realm of possibility. If we have a couple of bad quarters, that could happen. It might go up to 1,000. I'll be really pumped if that happens, and it could happen. Who knows? If we have a couple of great quarters, that's plausible. So there's a group of statisticians that wants to tell you that all assumptions are bad, right? I don't want to make any assumptions because what if I'm wrong, right? Well, here's a model that essentially makes no assumptions, and because it makes no assumptions, it's unable to kind of build on anything, and so you end up with, well, what could happen? Anything could happen. Well, not quite anything. That's not quite plausible. Here's a model that's still very flexible, but it does make some assumptions. And by making some assumptions, it's able to kind of give you more plausible error distributions that are a little bit more believable. So that's one of many, many, many cool things that this BSTS software can do. But I think I've probably overstayed my welcome here at this point. So let me wind down. Other cool stuff the BSTS the software can do. If you have daily, so you have very fine-grained data, so you have hour of day patterns and day of week patterns and week of month patterns and things like that. There's a way to allow you to fit multiple seasonal patterns there. One of the assumptions of the state space models is that everything in sight is Gaussian, right? All those states have normal distributions and the data have normal distributions and stuff. Through the magic of data augmentation, BSTS allows you to think about data that is small counts of things and success failure things, and if there's occasional outliers in places and things like that, you can fit student T errors. Orthogonal data augmentation is a really kind of cool idea on the regression side that can sometimes be more efficient than the algorithm that I described to you. There's like some other cool stuff that you can do. BSTS has been very successful at Google. It's also attracted a considerable amount of attention outside of Google. And what I'm showing you here is just some headlines from the data science blogs and things like that, where people are actually using the software, which I think is quite gratifying. So let's see, conclusions. What did I say here? I talked to you a little bit about data, right? I gave you a little introduction about Google Trends data. The Google Trends data is super duper useful if you need to be able to measure how interested the public is in certain types of categories. You can either use the specific categories from Google Trends. If you have a particular search term you care about, you can get that from Google Trends. If you want a big list of individual search terms, you can get that from Google Correlate. Well, how was this data useful for us? Well, we in the two examples that we saw, we didn't actually need the data until we hit the financial crisis, and then the data turned out to be really useful. If you have a time series and it's easy to predict, then the Google data is not going to help you. But if you have a time series that experiences like big bumps and changes, and you're curious about what changed during, what caused those big bumps and changes, then the Google Trends data, I'm assuming your time series is related to something that the public cares about, then Google Trends is a good way to sort of uncover the source of some of those things. I talked about two different components of the model. There's a time series element to the model. There's a regression component of the model. The time series component of the model was important because we needed to be able to kind of structure our models so that sometimes we have a seasonal component and sometimes we don't. The spike and slab bit was important because when the regression component of our model had many more predictors than we're able to handle with sort of a standard OLS type regression. And so spike and slab gave us a truly sparse posterior, but not a sparse posterior where we tried to do the impossible thing of finding the one best model in our 22-ton block of carbon. We're able to kind of average over a bunch of different models and end up doing a better job because of it. And finally, the one thing that I'm a little hopeful for, some of you that are interested in doing time series models might be inclined to maybe pick up this BSTS software, which you can download from CRAN, and just sort of play around with it and see if you can, hopefully it'll be useful in some sort of time series modeling problem that you might have in your own work. With that, I've got some references, but they're too small to see, so I'll just stop here. Thanks.
It's working, yes. Okay, so thank you very much for this brilliant presentation. I am very happy to see so many students, so you can understand what is research at Google. And okay, we have time for questions, comments. So there is a lineup of professors of economics and statistics. So I believe you should start, and then we can take also some general questions, if you like, about research at Google. Guido.
Just two questions. Can you say something about the risk in doing what you are telling us about Google Trends and other aspects of Google about the spurious correlation? That's the first question. The second one is slightly more technical. Does BSTS, does the software allow for the possibility of multivariate responses? Because occasionally we might be interested, say, in stocks for different markets or stocks for different countries, and rather than analyzing them separately, we would like to analyze them jointly. So that would be like for clustering and stuff like that.
Yep. Okay, so two questions. One is spurious, the other is multivariate. So yeah, the big risk in spurious predictors aren't a super big risk as long as there's human supervision of the model, right? So if you do one of these automatic variable selection things, and it's there to kind of help you pick out what's good and what's not good, if you have some domain knowledge, you can sort of, some of the names of some of these things will be red flags, right? So I think the big risk is that people at Google like to build systems where the computer will go off and make a bunch of decisions and we don't have to get the human involved, right? Now, how big a risk that is, I guess, depends on who's using those systems and what for, right? A lot of the systems get used at Google for making ads better, right? I want to make my ads better, right? Well, if I make the ads better for 80% of the people and it's like completely screwed up for 20% of the people, then I guess on balance I did something good, right? So my spurious predictors, even though they really screw up sometimes, a lot of the times they're non-spurious and things are better, right? We got in a little bit of trouble, and you saw this the other night when we built a system to automatically predict the value of the flu, right? So Google had this thing called Google Flu Trends that was supposed to be tracking how many people have the flu in different areas, and we ended up with a spurious predictor in there that was, for a while, kind of tracked the flu, but then at some point they became uncoupled, and then our predictions for the flu went off the charts, but that actually wasn't happening in real life. So one of the differences between, I think, the statistical way of thinking and the machine learning way of thinking is that the machine learning guys are going to build it and they're going to go for it, right? And sometimes it's going to do great, and sometimes it's going to fall apart, and that doesn't seem to bother them that much. I think we tend to be a little bit more conservative and say, well, I don't want to say that this is predicting that thing because it might be wrong in the future, right? We're a little bit more timid there. So it's hard for me to say more concretely anything about how bad a spurious predictor is because you need some context for the, I certainly hope we're not going to do something like that in the self-driving cars, right? That would be a terrible time to have a spurious predictor, right? For some sort of economic analysis, yeah, okay, maybe it's kind of marginally bad. The second question that you had was about whether BSTS can handle multivariate prediction. And the answer is no, but it's awfully close, right? And so let me tell you about this idea that's been sort of floating around coming out of the Mike West school of time series modeling, which is for really highly multivariate time series, what you can do is you can think about modeling. So I've got y1, y2, y3, y variable 1, y variable 2, and y variable 3 at time t, and of course 3 goes down to 10,000 or something, right? A lot of these things. Well, I can model any joint distribution as the marginal distribution of thing 1 times the conditional distribution of thing 2 given thing 1, right? And I can think about doing that for time series models, right? So I can imagine fitting a BSTS model for the first variable that you cared about, right? And I can imagine fitting a BSTS model for the second thing that you cared about, where the first thing was a regression, right? We're using that as a predictor, a contemporaneous predictor. And the third thing given the previous two. And this is kind of a natural and exciting use of BSTS because the regression that we're using has a spike and slab component in it, right? Multivariate time series gets really, really, really hard if you have more than, 12 or something like that predictor variables, because you have all these different variances and covariances floating around, and there's a real need for sparsity, right? Modeling the covariances of a multivariate time series is equivalent to modeling a set of regression coefficients, right? And so, what the multivariate normal distribution sort of tells you how to turn covariances of y given x into, regression coefficients of y given x. And so, if you think about modeling the second thing given the first thing and the third thing given the preceding two, and sort of a scaled up version of BSTS, then there's a little bit of work involved. It's not something that works like straight out of the box, but if you wanted to use the software to build a series of parallel models like that, you could do it, and the spike and slab bit would sort of help you kind of only get the kind of marginal covariances that were the important ones. They would come to you as regression coefficients, but you could then turn them into covariances if you needed to.
Questions or comments? Okay. One hand. Okay.
I was wondering, is there any possibility for a multi-level extension of this kind of models? I mean, imagine I have a time series for a guy and for another guy and for another guy, for another guy. And I know that parameters are somehow similar, but but I want to estimate. So I want a part of the model to be similar for everyone and some variation according to the participant.
Yes. So so you asked the question as if, is there the possibility that such a model exists? And that's not the problem. The problem is there's sort of an infinite number of models that could exist. There's a very large number of ways that you could take the structural time series model that I described to you and write it as something that would apply to a vector of y's at each time as opposed to a scalar y, right? The framework is very, very, very flexible. And the fact that it's so flexible is kind of a problem because you can do anything you want to, right? So how do you want to describe this multivariate process? There's a thing out there called a dynamic factor model, which is essentially the same thing that I described up here, except, y is a vector and, it's got some sort of a structured relationship with some common state that's shared among all the different, so there's one local level model, and then there's a set of coefficients for that local level model that blow the state up into the mean for y1 and the mean for y2 and the mean for y3. With multiple y's, I guess you could have a couple of different local levels floating around so then the question is, how many local levels do you need? It's probably fewer than the number of y's that you have, but is it half? Is it 2? So things get a little bit more complex there, right? If you have a particular economic theory or econometric theory in mind, you can probably express it in this framework, right? If you don't have a particular econometric theory in mind, then I would be inclined to take your multivariate problem and approach it the way that I described to Guido about how I would model things. The easiest thing for you to do with the software as it stands right now, if you have a multivariate problem, is model the first guy, then model the second guy given the first guy as a regressor, and model the third guy given the previous two guys as regressors, right? And then, that'll be a relatively easy thing to do, right? If that doesn't work for you, then it's because you have a particular idea in mind about how these guys are supposed to share information. And if you have that idea, then it's possible to express it mathematically, and we could build it into the software in a similar way. But taking the software as it stands right now and doing that is not possible.
Okay, we have time. Francesca?
Yes, I just have a curiosity maybe about the second case that you commented on data retail sales. Because in that case, you were working on deseasonalized data. And
Yes.
my question is, why, if you have a tool that you described able to model seasonality as well as modeling linear trend, as well as modeling regression, you, in this case, were starting from deseasonalized data?
Yes. Why did the Y variable started off deseasonalized, right? It was deseasonalized before it came to me. And then I've got 630 categories plus 100 Google predictors, running kind of 700 MCMCs to use my tool to deseasonalize things seemed like a bit of overkill, right? That just seemed like it was a little bit heavier than what we wanted to do. So there are tools in R for doing just the time series. If you just have a basic structural model, a local linear trend plus a seasonal effect, you can fit that in base R. There's a function called struct_ts. And so what we did to do the deseasonalization was we ran all of these Google queries through struct_ts. We figured out what the seasonal component was from struct_ts and just subtracted that off. That's how we did sort of the poor man's deseasonalization. I think that there's something that we missed there. I think that the deseasonalization that we probably should have done was subtract off the seasonal pattern. Well, given that it was already deseasonalized, I don't know a better way for us to deseasonalize. There's a related question, which is if you have data like the initial claims data that does have a seasonal pattern, should you deseasonalize there, right? Because you do have a model that is already going to explain the seasonal component of your Y variable. So, should you then go off and should you suck out the seasonal pattern of your X variables, right? So you'll look at the surprises in X giving you the surprises in Y. That's what you hope to find. But then I get myself kind of confused when I think about that because, well, should I be subtracting off the seasonal component that each X variable has in its own seasonality? Or should I be trying to subtract off the projection of the seasonality in the Y variable from the X variable? Because the seasonality in the Y variable, that's the part that's already been explained, right? So I don't need that bit in the X's. Maybe there's a projection of that onto the X's. Maybe that should be the thing that I subtract off from the X's and use that notion of deseasonalization. And I just have never gotten around to exploring that question. Right? I sort of think that there's probably an opportunity for the BSTS software to automatically deseasonalize the X's by subtracting off the seasonal pattern that you found out in Y and regressing the Y on that seasonal bit. But I haven't done that.
Okay, maybe a last question, if any. Yes?
So also, I have a non-technical question. I was wondering to which extent it would make sense to apply a model like this to very fine-grained time series. So I'm talking about the setting where I don't have sales and unemployment, but I might have a stress level and data from an accelerometer and ECG signal. So something I can change in a time span of 10 seconds, and every second I have 100 samples.
Right.
Would it even remotely make sense to use a model like this to model and even predict such a fine-grained event?
I think it would. I would want to make sure I could take a look at the time series that you're describing. I'd like to see a plot of it first before I commit and say absolutely it would. But yes, I mean, these state space models have been successfully applied to all kinds of different time series. And there's some very useful types of state in your state space model that I haven't included into BSTS that probably would describe the type of data you're thinking about. Sometimes that type of scientific data, the relevant characteristic is oscillations, right? And sometimes it's the frequency of oscillations is what you care about, and that's sort of changing. So there's I mentioned that one of the state components that you can fit here is an autoregressive process. The autoregressive process is something that we normally think of being as operating in the time domain, but the autoregressive process can be projected into the frequency domain. There's a time-varying version of the autoregressive process. So there's an AR process where the AR parameters themselves move throughout time. And if you think about that time-varying AR process as something that you could, kind of point by point in time, say, well, now the relevant frequencies are this, but now the relevant frequencies are that, then that winds up being super helpful. And if that's the situation you find yourself in, if this is an actual problem that you have, there's a book by Raquel Prado and Mike West that that basically does exactly what I just described. So it's the Prado and West.
Thank
Prado,
you.
Yeah.
Okay. Maybe a final question, if there is any. Okay. If not, we thank you again, Steve. Okay. And yes, there is the aperitif outside.